For over 2,000 years, number theory has operated under a single, inescapable constraint. To find a prime, you must first attempt to divide it. This reliance on physical numerical values began with Euclid's early proofs on prime infinitude. While he used geometry to prove they never end, the actual detection of primes eventually shifted into pure, value-heavy arithmetic. Because division is an empirical process that must be repeated for every new number, the distribution of primes appeared inherently chaotic. G.H. Hardy and other 20th century mathematicians viewed this unpredictability as a foundational property of the number line. Even modern deterministic breakthroughs, like the AKS test co-authored by Manindra Agrawal, are computationally restricted. These algorithms operate within polynomial time bounds, specifically big O of log n to the sixth power, meaning processing time scales significantly as numbers get larger. Prime calculation inevitably hits a computational wall because it remains anchored to value-based division. As the values scale, the energy required to process them eventually exceeds the limits of traditional arithmetic. In 2026, Hedi Zarkouna introduced a different approach in his paper, The Index Theory of Prime Numbers. He proposes a system that eliminates traditional arithmetic entirely, replacing it with an absolute spatial geometry. It algebrizes the Wheel of 30, a classical filter for multiples of 2, 3, and 5. Converting this circular heuristic into a linear equation creates a 2D coordinate space. Stripping away physical values leaves only spatial indices, fixed geometric points representing the number line structure. When the focus shifts from a number's value to its location in space, arithmetic chaos is replaced by geometric determinism. Building this system requires three specific algebraic expressions, starting with a way to map values onto the spatial grid. This absolute generating function, f of m, bridges an index n with its exact coordinate. The -1 to the power of n acts as a parity alternator, ensuring every odd or even index aligns perfectly. Plotted on the grid, irregular prime gaps become uniform, predictable spatial steps. By establishing this absolute base layer, the index theory creates an environment where numerical values no longer dictate the rules of the calculation. With a grid established, we need a way to identify composite numbers without reverting to division. The spatial intersection matrix, phi of p and q, identifies composites by tracking generator paths. Where lines p and q intersect, a composite coordinate is marked. Crucially, the spatial intersections function equals the generating function's product, directly linking geometric location to underlying factors. Composite status is a structural property of the coordinate's location on the grid. If a point sits on an intersection, it is composite by definition. Identifying these coordinates is only the first step. To find primes efficiently, the system needs a way to navigate this space at high speed. The spatial exclusion function, or jump engine, uses floor functions and the constant 2p minus 2 to calculate exact distances between nodes. It leaps mathematically over known composite intersections, landing exclusively on untested prime coordinates, entirely bypassing trial division. Because it operates on geometric distance rather than trial division, the jump engine never wastes computational power on numbers already known to be composite. To test an isolated, massive number, the system uses a final mechanism, the algebraic viewfinder. The retro-index function, n equals the floor of n divided by 3, projects any massive value directly onto a precise spatial coordinate. The viewfinder then validates it through spatial non-existence. If no composite intersection lines pass through that exact empty coordinate, it is inherently prime. Since this process targets the coordinate through a direct formula rather than a sequential search, it achieves a local time complexity of O of 1. This means the time required to verify the coordinate is constant, regardless of the size of the original number. By utilizing this local constant time projection, the index method removes the polynomial time scaling that limits current deterministic tests like AKS. When we apply these expressions at scale, the prime distribution is no longer a collection of random points, but a perfectly structured geometric matrix. This structure enables a secondary process, the natural factorization theorem. In this system, every composite coordinate is the result of the intersection function phi of p and q. Because the coordinate itself is defined by these variables, a spatial breakdown of that point immediately reveals the p and q lines that created it. The factors are not searched for. They are the structural components of the coordinate. This approach changes the cost of factorization for cryptography. Current security relies on the assumption that finding factors through value-based division is too time-consuming to be practical. By replacing the 2,000-year-old paradigm of Euclidean division with absolute spatial geometry, Zarkouna's index theory provides a new framework for analyzing the mathematical structure of prime numbers.